Okay, so finally back for another piece of this hash table thing. Um, so last video, which I haven't uploaded yet, but the audio was quite bad, very crappy. I'm not really sure why, but this time I'm gonna try to record with this headphone or heads, yeah, whatever they're called, headphones, with like this speaker thing. So hopefully everything will be better and not worse. Let's give it a shot. So there's several things I want to yeah try to do today. Hopefully they will come out well. Um, so yeah, let's see how it goes. So let's get started. So I'm gonna start with some very simple things. I'm just not gonna maybe yap too much about it, but technically these things here. So yeah, like this doesn't really need to be part of the hash table itself. So what I want to do as well is just benchmark these two against each other. Um, so I'm gonna do that. Um, yeah, before I can also rename because this is actually like double. It's called double hashing. It's kind of like the technique being used. And this, yeah, I'm gonna just move up. I think here would be fine. Okay. We're just gonna call this one here even v hash lib. Let's see where the problem is here. Okay, double hashing. Perfect. Okay. So here, yeah, I also want to try to just make this real quick into a simple for loop because basically, yeah, I don't want to waste here like, yeah, this thing not being used. Um, okay, key. Um, then I can basically copy something here similar to ah, okay. FMV prime. Okay, perfect. So that is it. Maybe I can put here like custom fin1a hashing. Okay, nice. Okay. So I think I'm gonna use this space. So I wanna, yeah, basically benchmark also these two against each other. Um, so let's do that because I didn't do that in the previous video. So um, what was the thing? Yeah, B testing. Okay. So let's do this thing. Okay, and let's do this 1,000. Maybe I don't know 50,000, and let's do 1 million. 1 million. Okay, so there it is, 1 million. And it's the other b.run, the name of this particular test. So yeah, what I'm basically doing here is going to test with different key amounts, and I'm gonna run that. So I'm gonna say here keys and total keys, and then I have here this func. Oop. B testing dot B. Of course, it needs to have a pointer. And oop, here. Oop, okay. And I think if I remember correctly, make string, and here will be total keys. Total keys. Um, okay, so here I'm just gonna assign some temp stuff for now. And here, so creating here the keys. So after this is done, I wanna b.reset timer. Reset timer. And then here, I'm gonna do b.n. And then here, loop through the actual keys, and then call the fnv hash function. And here I will have this string. And I'm gonna do basically the same for the other one. And then this will be fnv hash lib. And why is this complaining? Undefined, what the hell? Okay. Ah, okay, I know why. It's because I forgot to remove this sucker here. Hash lib. Nice. Okay. Um, so one thing I want to do is just for this because previously I've been using like these yeah crazy foo stuff, but I think would be maybe better I think to just use like a GUID and keep all the tests with using a GUID. I don't know, I just have a feeling seems like better than just using these like random foo keys. Um, so let me see. I need to. Can I open an let's see if yeah new incognito window. Cool. So let's do this. Um, so GUID library and go. GUID package. Here we go. What is this? Mm, 16 byte GUID. Let's see. Ah, I thought it was a GitHub. Oh, okay. Let's see what the fuck is this. Oh, okay, I see. Uh-huh. String. I don't know. I'm gonna give it a shot here. Um, I forgot how to install these packages in Go. And well, also let's see if there's other stuff. Seems pretty straightforward. GUID package. Well, there's a lot of stuff actually. 16 byte, 32 GUIDs. Fine, I'm gonna stick with this one. So let's see. Package. No, I forgot how to do that. Shouldn't be go install. I don't remember what go install. Is it? Go install help. Maybe go install and then this crap. Let's see. No record model price package. Go to edit. Go get. Let's see. Go get. Uh, let's see. Oh yeah. Okay. Cool. I think it did install it. So GUID.new probably. Let's see. Probably like this. So let's see. Printf GUID. Okay. Yep. Here's the GUID. Nice. So that's it. Nice, nice. So I'm gonna refer to changes here. Close this. Ah, I could have copy pasted. Fuck. Okay. So, ah man, that was a stupid thing that I did, but it's fine. Let's get this thing again here. And okay. Now, one thing that I didn't test is if this will generate a different one, or if I have to like, I'm not really sure. So let's see, something to test. Something to test here. Come on, I don't want to comment this out. Hmm, maybe I can say b.log. Do I have that? No. Where was the log thing? A log f? b.logf. And why am I not getting completions here? That's weird. Mm, okay, fuck it. FMT. Let's see. So GUID. Okay, so let me see. Maybe I have to comment this out as well. And let's see the command. Let me see if it will let me run it with this one. And malformed import path. What the fuck? Double slash. Maybe it's this. No? Testing. Maybe I didn't like this shit. The fuck? Come on. Where's the example? Okay, cool. So it was like it was before. Oh, there it is. Okay. Let's see. There's no field or method, new string. What the fuck? Why? Ah, okay. Dot string. There it is. Okay, let's see. No test to run. Fine. So this one then. Shit. Ooh. New line. Let's do it again. And yep, as I suspected, this is using the same one, so I have to go like this. Now let me run it again. Yep, there it is. Okay, nice. So I have this thing here. I can get rid of this. Okay. Cool. Nice. Okay. Whew. So let's do this. I want to see if I can, in fact, I don't know, can I do this? Not really sure how to specify multiple ones. Would this be possible? Nope. Okay, let me try. Maybe the comma separated? I'm not sure if that will work. Go test. Oh, come on. What's this shit doing? Let's see. Interesting. So let me ask Perplexity, or before doing that, let's say how to run uh, specified benchmark tests in Go. Let's see. Nope. I'm wondering if maybe could it be possible if I go like that and maybe like this, Sounds pretty intuitive. Come on. Go test. Let's do it. There it is. Lib. Okay. No, it doesn't run it. Fuck. Okay. I'm gonna just four speed get in perplexity. Do with perplexity. Fix the following. Go command. Let's do it. Look at this. Cool. Would have never guessed, actually. Would have never guessed. Nice. Nice. So one thing. Okay. So I'm gonna put here. So to benchmark uh, multiple tests. Okay. Bench mem. Uh, let's go for maybe 100x. Not sure how long that is gonna take. Hopefully not very long, but so this is interesting. So let me just make this into a table, but let's do this. Bench into a nice table. Um, let's see if also it gets also the details of the thing of the test. Nice. Okay, so I'm gonna say it into separate tables. And let's say convert to yeah, 10. Okay, convert to okay, no, I think that's fine. So okay, so let me see if I can write this down here. So benchmarks. Um, FNV1A times. So so from Golang's goes library and no. This is actually wait a minute. It's actually this was what I was. Oops. Wait a minute. Yep. So it's goes down the library and um, my FNV 1A implementation. Nice. So definitely what I can see here is that um, this one, so like my own, I don't know exactly why, but my own FNV1A implementation is much, I'm just gonna put also like, it's so trivial. It's not like really something special that I'm doing. So my own FNV. So it's much, I don't know why, and I don't know if I'm really like benchmarking correctly, but it's definitely like way faster, right? So for 100 runs to insert 1,000 keys, it basically takes 11,288 nanoseconds. Um, and then here's like 12 million nanoseconds, but also that sounds like a lot of time. So let's see one moment. Milliseconds, so just to make sure. So for example here, yeah, okay, fine, actually no. So yeah, no, it's actually not, yeah, just looks large here. So yeah, 12 milliseconds, 0 point something milliseconds. Yeah, 0 0.011. And this will be like 0.6 milliseconds probably. So yeah, this one is actually much faster. This one is much faster. Okay, nice. And then one thing also, like, I remember I wrongly said that this was going to give, or this is potentially giving like a lot of like extra allocations just by the fact that, maybe if I move this here, that this thing, so um, fnb hash lib, that I would basically instantiating a new basically interface per operation. But it doesn't seem like it's, yeah, basically having any allocation, which is quite interesting. Um, okay, so the other thing I wanted to try, oops, the other thing I wanted to try is the following. No, yeah, oops. So, so if I have here in data, so technically speaking, um, yeah, this is like not really needed. So if I like the is soft deleted, there's like some, I think ways to remove it. So if I go to main.go, I'm just gonna copy this. It's here for a moment. Um, and then I think there's something also unsafe. Let me also say go format. Come on, come on. Ah, it's go FMT. Go FMT. There it is. So there is a way, I'm gonna just comment this crap. Why don't I just comment all of it, in fact. Well, this I'm gonna remove, this I'm gonna remove, and this I'm gonna comment out. Save dot size of data. What? Well, node maybe? Node type is not an expression. Mm, well, okay. So Golang unsave dot size of, let's see. Come on. Examples. Unsave size of. I don't know what's wrong with this. Um, okay. I think I know why. Node probably is it? Mm, what would be the syntax? I don't know. Do I have to instantiate this shit? I thought it will just grab it right away. Wait a minute. Come on. Okay, let me just go and see what's going on. So let's go again to this shit. Um, get the size of the following struct. Unsafe size of it's because of this? The hell? Come on, this is crazy. Okay, so size. Okay, there it is. Fine, fine. So this is basically the same. Yeah. Okay, so I'm gonna just basically see the size of this stuff, right? And it's gonna be go run. Yep. So I see here that it's basically 40 bytes, right? And you will be quite surprised. So if also I'm just gonna go like this. So the yeah. So 16, right? 16, and then I think those any type is also 16, and then of course bool should be 1 byte, right? 1 byte. So in total, let's say technically speaking, this should be like right. One would think. So this should be, let's say, 16, 16, 32 bytes, right? And this should be basically plus 1, 33 bytes, right? But it's actually 40 bytes. And basically the reason for that is because um, for basically something called padding. Um, so basically, I mean, the topic is a little complicated, but basically how why padding is being used. So for example, my machine is a 64-bit machine. Um, and then on 64-bit machines, we basically can read 8 bytes at a time from a cache line, right? And that's basically the maximum read data the processor can make when reading data from one of these cache lines. And so the reason for this to be like for for padding to be used, like, so the idea is like a trade-off. So you use more memory as seen here, but then you optimize like some cycles, memory cycles to fetch the data completely. So it has like something called like padding, and I don't know like yeah. So it's like I think yeah extra bytes. So if this would be, for example, um, let's say if we make up something here, so like the first thing here will be from 0 to the first 15 bytes, and the other thing will be from 16 bytes to 32 bytes, right? For the value. So those basically are the byte offsets. And then the other one will be from 33 to 39, right? So let's say those will be like the byte offsets. So like if there's like some type of memory address that's like, I don't know, let's say it's like something like that, right? And then something like this, and then so on and so forth. And then we have, for example, here 015, right? So this will be all the key, and key, right? And then in the next one, this will basically be 16 will be value, um, value, and then this will be, let's say until 32, so on and so forth. And then we have the byte which starts here in 33, sorry, the Boolean, so is soft deleted. Um, and then we will have, basically this will be 34, and oops, then this will be like padding, right? So that will be 1 byte, 1 byte, etc., etc. And then this is going to be, let's say, 35. And then it's going to be 39, right? So in this case, that's like the structure of that, right? So basically, what this will do is that the processor can read um, basically these values in chunks of 8 bytes. It's basically more efficient because um, basically it's always going to read in, let's say, one aligned axis the whole basically member instead of basically having that split around. So basically that's the reason we have these things with like padding. So the compiler adds this, and it's like also very dependent, I believe, on the architecture of the machine. So I think, for example, on 32-bit machine, instead of being like 8 bytes the word size, it will be 4 bytes the word size. So this is basically the basic premise. So if I could shave off, let's say, 8 bytes of memory from this basically struct, so that struct again can be potentially added as like for 1 million times or 2 million times, large quantities. So that can be a small optimization that can be done to minimize the memory footprint of the overall hash table. And so yeah, so technically, if I go back here to the hash table, this can be deleted. So if I remove, so maybe before doing that, let me think good time to commit as well. I don't know, maybe feat installed. What's the name of this library? So okay, do this to create GUIDs for keys to be used inside unit tests. Okay. And then here I can just say added it added tests for custom benchmarks fnv 1a hash station and for Golangs and for what's the name of this thing now? and for standard library in Golang to compare performance. And I would say custom implementation is much faster. Okay, cool. So I think that's it. Why not push? Why not push that thing right now? Nice. Okay. Okay, so this can basically be deleted. So let me go to the specific thing. So basically why things are marked as soft deleted, um, or why things are like basically not really deleted right away in this type of collision handling in hash tables is because you create like some sort of like chain. Yeah. So if you're trying to find something, so let me just like, maybe it's easier to hate drawing in this thing, but because it's terrible. And wondering what is Paint 3D. Oh, look at this updates. I really need to change to Linux as well. So that's in my to-do list. I think Microsoft has a lot of annoying stuff. I know it sounds cliche, but it's really annoying. And they're also putting Copilot everywhere, which is really, really, really annoying. Even like in Notepad, there's Copilot. Look at this. This shit takes forever. I can't even move it. It's like the process is frozen. Can I say control panel or what's the thing here? Performance monitor? Is it? What? It used to be performance monitor. Oh, let's see. I just want to see how much CPU is using this shit. Resource monitor, that thing. Let's see. I just want to test. Okay. I thought it was gonna like spike pretty low. Okay, fuck it. Well, it stays the same. Well, at least they're not like eating up the CPU. Okay, so paint. Small parentheses. No, paint. Come on. And then this fucking app is so terrible to even draw in as well. Look, you have, that's what I'm saying, like fucking Copilot here as well. Jesus Christ. So invasive. Anyway, so we have, basically here's like the, apologies again for this really bad drawing. So here we have like the, right, the different like slots and so forth and so forth. So the way kind of like hash collisions or like kind of can be visualized. So let's say it's, I don't know, something here is like occupied, right? Occupied, and we want to try to put like a key here, right? Some key, maybe maybe this can be like just, right. So let's say I have a key, and this key like hashes to the same place. Well, this is occupied. So let's say the next, I don't know, the next one would be like I don't know, this slot here, for example, this slot here. Um, so when we're gonna basically search for the thing, let's say we insert it and then we want to search again, right? So we first search here, so it's one collision, so it recomputes the hash function with the double collision or the key with that basically double collision um, hashing technique, and then it's gonna basically go here, right? And say, oh, okay, it's found it, right? But let's say like somebody comes and says, oh, like, okay, this key thing, like the same key here. So for illustration purposes, let's say this key is like F, right? And let's say this key is like, I don't know, um, like G0 or something, right? As just as an illustration, G0. So let's say somebody like in another operation, or not somebody, but let's say we're gonna delete this item with this G0 key. So if we were going to delete this thing, and let's say this thing is empty, and this will be like an empty slot, we'll basically say, nope, this doesn't exist, just because of how we are doing the test. So if I say like search, right? So if I say search, right, and I say item that value equals null, it basically key not found, which is basically not the case because the key is here. So that's why like it can't be it can't be totally deleted because it will break the chain of um, basically of those values. So that's like in essence that's how we're handling collisions. It's basically those nodes that have like that collide, that have like hash collisions, are basically related to each other and kind of like these types of chains, right? So this is related to this, and let's say that I don't know, there's like another key. Let's say this is like I don't know F dash one or something, and let's say this was here, but then for some reason like the next let's say position it was done here. So then these things are related to each other, right? So we need like the always the previous thing in the chain um, to be able to go to the next one, right? And to the next one. That's why basically we don't delete completely. It's only basically deleted when the table is resizing up or down, because then it doesn't make any difference because we're creating the new hash, um, basically keys anyways, the new homes for each node, right, to live in once again. So that's basically the explanation. So yeah, so let's go back. I would say, where can we insert? Yeah. Um, so yeah, so one, in essence, like one thing that we are, if I go here to delete, this is basically, what this is basically is known like as formally as tombstones, I think. So tombstones hash tables, right? So tombstones are used to mark deleted elements, allowing the table to maintain correct search and insertion operations, while also enabling the reuse of deleted slots. And actually, that's something that I am currently not doing, in fact. That could be something also quite interesting because reusing, um, yeah, things that have been like technically deleted as well. And then going back to the diagram, in fact, let's say this has been marked as soft deleted, and then still if we have another key, so for example, I don't know, like HF or something, HF, that also like collides, has a hash collision with like G0, it doesn't make a difference if then we replace it here, if we replace the contents, because the chain still basically maintains its properties. Okay, so actually that's another thing here to do. Um, so where can I maybe say, okay, so to do reuse delete, soft deleted cells when collision when inserting. So let's write this shit down in the corresponding place. So insert. Okay, I'm gonna do it here. Okay. So let's do this first. So search. So I can say like if value is not nil, I think would be the same. And item.value does not equal nil. Because I think one of the things like it can be done is when we soft delete, so let me not get too much ahead of myself here. When we are deleting, I can just say instead of this, I can say value, and I can set it back to nil again. I'm wondering if, just as an experiment, what will make more sense? No, I think I cannot do nil now because it's not a pointer. It's not a pointer, and I don't want to have a pointer to the string because again, what I was explaining in the previous videos, that will create like a lot of more potential cache misses because we have to like go hopping around in memory, and that's what we want to avoid. So this is the most reasonable thing for our implementation, or for, I don't know if our implementation, but this my implementation or the implementation. Um, so here, and I know value does not equal nil here, okay. And then we go here, item dot value equals nil. But first of all, I want to do, I got too much ahead of myself actually. Too much ahead of myself. So before that, before I do this, actually, before I do this, okay, wait a minute. I have to kind of like rewind myself because I should have benchmarked. Oh shit. Uh, so search. Okay. Oops. Okay, so I'm gonna go to search and where is it? Where is it? Come on. I'm gonna revert this, and I'm also going to, come on, revert as well. So let me, okay, let me just commit this thing. So um, refactor renamed hash to double hashing made fnv hash and fnv hash lib not instance methods of hash table as they don't need to be. Okay, fine. Cool. So that's that. So now I'm gonna go back to insert. Okay, well, there it is. Okay, nice. So, whew, getting too much ahead of myself. So let's do this. Okay. I think I was also benchmark non-existing key, search key. Where is it? Insert nor resize. Okay, and let's do also the. I want to do the GUID stuff here. Come on. Oh my God, yeah, there you go. Copilot again, creeped up. Probably entered a weird hotkey. Your mom. Your mom. Want to turn this into a roast battle, or shall we pivot to something more enlightening? I've got trivia, deep thoughts, or weird history facts ready to go. Your call. Oh my God, look at this. Jesus. Anyway, um, there you go. GUID. So let's do this shit. GUID.string. Okay, nice. So there it is, 2 million keys. I know that's the length, 1 million keys. Okay. Um, okay, cool. So, look, and then here I still left the traces here. So with pointers to structs to 255, with actual data structs 222 milliseconds. Basically, on average, to insert a million keys over n times. So let's do this again. So go test bench, and let's do this. Let's do this, and let's do that, and let's do 100 as well. Whew, taking a long time. Come on. Damn, 30 seconds. That's insane. Takes too much. So let me try 50 maybe. 50. Just to see like if it makes such a big difference. Trying to find the sweet spot. But I think I've done 100 in the past, yeah. I've done 100 here in the past. So I think this is 271 milliseconds. Let me see. 271 milliseconds. 271 milliseconds, correct. 271 milliseconds, and then this is like 10 megs, I believe. So bytes to megabytes. So this should be, yeah, 10 megabytes. Whew. Yeah, no, it's much better to do over 100 times. It's quite different. So 282 milliseconds versus 271. Okay. Um, nice. So let's continue this. So this, okay, I'm just gonna put this stuff just quickly here. Um, oops, no, that's not the one I wanted. It's this one. Cool. So this is with Okay. And one thing I, yeah, now I remember. One thing I was important to do is basically in the README. So um, machine specs. Okay. And then I guess AMD 64. Windows. Boop. Okay. There it is. Machine specs. Now let's go back to where I was. Okay, nice. So now let's get this shit rolling again. Let's get this shit rolling. Data. Okay, fine. Here we go. Delete this shit. Nice. So again here. Or item. Or item the value equals nil. Continue. Right? So that we're skipping. Oh, okay, okay. Whoop, whoop, whoop. So if item that value or item that value. No, no, no. So there it is. If item that value equals nil, there it is. Boom. Search. So item that value does not equal nil. Okay. There it is. And item dot value does not equal nil. So you go item dot key that equals key, and item dot value does not equal nil. The same thing here. And item dot value equals nil. So this is not soft deleted. So value equals nil. Okay. And then we say value equals nil. There you go. And okay, there it is. There it is. So before doing anything else, run the tests. There it is. Perfect. Everything passing. Side note, there is actually some duplicate code here that we can essentially recycle. So let me just see something really quick. So func, um, a small branch of the task, but I think it's nice. I think it's worth it because I think it can create a little bit of so delete. Let me see if this can be done. So a pointer to item. No, it's like this. Yep. Item that value equals nil. There you go. Load factor. Boom. Resize. Okay, so delete item. Let's do this. So delete h.delete item and item. There you go. So I'm gonna do this again here. Nice. And come on. This, oh, damn, this is crazy. This needed a, okay, interesting. I forgot this here. So that means it currently was never proving when deleting. Interesting. There it is. Okay, at least shit is working. That's nice. Okay, so I think I need to add here a to-do to test this shit when it's probing. Okay, so to-do test when probing. Okay, nice. There it is. Now lost sight of, oh yeah, yeah. Now I remember. Now benchmarking this shit again. Boom. I'm also benchmarking without resizing still. So I still need to benchmark with resizing. 30 seconds. Okay, come on, Copilot. Where are you? Copilot, come on. Your mama. No, come on. Your ma, your mama. Yeah, mama jokes. Oh my God. What a waste of compute, guys. Okay, so let's essentially copy paste this thing. Copy paste this thing, guys. This is the beautiful. This is beautiful stuff. So it is here. Faster. Not much. The weird thing, now the crazy shit is that it's faster, but memory is still even like a tiny bit higher. That is insane. That is insane. Interesting. Wow, and then here for some reason it went very high up. 275 milliseconds. That is yeah, that is insane. Why is it so volatile? Why is it so volatile? That's very weird. 263, it's like jumping a lot. I don't know what I should use. Yeah, no, this is way not so properly calibrated. So it's not good to let it just do one. Yeah, it's interesting. Well, okay, you know what? It's even, yeah, here is more memory. I can't really explain it. And I'm not really sure if my benchmarkings are working well or not, but I think so. I cannot see if I'm doing particularly things bad. But now let me go and see if I can reuse. So let's do that part like the reuse thing. Okay, yeah, essentially it is reusing it. So if it's nearly inserted already. Okay, by virtue of doing that. So, okay, so there's another thing I also want to do. Um, why is this complaining? Is unused. Why is this unused? Was it always unused? Compute next size up. Uh-oh. Okay, sidetrack again. Where is resize? Okay, sidetracked again. New size. Pick smallest length. Okay, wait a minute. I have a pick smallest length here. Pick smallest length. Uh-oh. Let me see. So get prime. Aha, pick largest length, pick smallest length. Perfect. So this shit. Okay, so again, let me just commit this shit. And so I again did two things. Bad me. So let's go here. So refactor. Refactored, repeated, code within, delete method, which delete item method. Okay, fine. And removed as it's not needed. Um, okay, quite a long commit, but that's it. Boom. Okay, now let's get here. So I'm wondering also, this shouldn't be here. Compute next size up. So this should be compute next size, actually. Where is this shit being used? Yeah, I think the reason why I am only using this pick smallest length. Actually, I think I have a small mistake. No, I think I do need to have next size down actually. No, so I think um, delete item. No, yeah, next size up. No, I have to actually do this. I'm pretty sure. So new length. Yep. So I'm gonna run the test again. Yep. Okay, passing. Whoop. Good thing that I noticed this stuff. Okay, nice. Oof. So commit again. Um, fix used instead of pick smallest length. ¿Qué pasó? No sé, yo te lo di. Yo te lo di. Pues yo te lo di en la cama. Pick smallest. Oop. Pick smallest length within. Okay. 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 So I think, yeah, nice. So I think everything is fine. There it is, test passing. So there's another thing, whew, going back again, keeping track. So I think I'm almost going to finalize this this video here. So one thing I want to do is, so if I go here to double hashing, so for example, like I'm just gonna control F. So this shit, of course, is being called many times per operation, potentially many times, right? And this thing here, so fnv hash, is also being recomputed constantly, constantly, which is quite inefficient. So one thing I want to do is kind of only pre-compute this once, um, and then I think one of the trade-offs that I want to do. So basically, what I'm trying to do now is having a trade-off for a little bit more memory, a larger memory footprint, but for the sake of speed. So sacrificing memory for more speed. That's the basically idea behind this. So as an exercise, I'm basically going to do basically the following. So if I have like a type, let me say, call it like key. So I'm gonna have the actual string and then the hash UN64 that's gonna be pre-computed. And this is going to be it. And I'm pretty sure it's gonna be also 32 bytes. Um, I know. Okay, 40 bytes. Fine. Uh, that's yeah, not really sure exactly why, but there must be some reason internally that Go will make this thing 8 bytes, which is a little strange. I'm just gonna try something, just fiddling and see if this size will change. Nope, the same. Okay. Anyway, so I'm gonna basically make something like this. Um, so let's do this. Nice. And it's gonna be quite simple. This should be quite quick, this operation. So insert. Okay, so I think I can do it inside this here. or no, actually insert item. No, no, no. So yeah, insert, I think. Insert, so here, um, I'm gonna say key, so value, it's gonna be, key, and hash is gonna be fnv hash key. That's basically what, oops, shit, what this is going to do. And here, it's basically confusing itself here. Um, what can I call this basically? Maybe, let me just say node key, maybe node key. And yeah, let's call this also here. Okay, yeah, K. There it is. So node key. There it is, node key. So double hashing, node key. So this is going to be deleted, and I'm gonna say node key dot hash. The fuck. This is strange. Node key hash undefined has no method hash. That's strange. What the fuck? Why? This is weird. Okay. Think this is a fucking method. I don't know why. I have no idea why. No idea. Okay. Key. node key. Perfect. I don't know why the fuck. Key dot value, and then we say dot value, node, node key. Okay, that's that. Okay, so okay, so this is interesting actually. Not sure if I can do it this way, in fact. So dot, not sure if I could do it this way. Okay, let me just. I think I also need here maybe not sure if this will be actually. Let me see. I'm not sure. No, I'm not convinced. So value. Um, this is actually K. Can keep it as key. Okay. And here for search, I have to do the same thing. Maybe we'll create like a small method. Dot value, key, dot value. And the last one This is the shit I don't understand. Ah, fuck. Okay, say key. Blinding. Blind here. Okay, so should be like this. Well, yeah, or hash key actually. So hash key here. So that should be all. Go test. Hash imported but not used. Okay, let's run it again. Undefined key. Where is it? Ah, yeah. Are all of these failing now? Ah, yeah, yeah. Fine. Let me. Fine. Node key. Why not? Oof, nice. Okay, they're all passing. Oof. Okay, so now kind of moment of truth. I mean, the thing why I'm doing it here is that I don't want to make the thing calling this code basically have to create this object. So I'm doing it inside these methods, and then of course I need to create this one time here because the idea is to like not have to recompute this thing every single time. But let's see if that will work. So and well, let me just run this thing. Run. Boop, boop. Okay, let's see. Whew. Okay, Copilot, your mama. Your mama. Come on, look at this. Come on, Copilot. 259. 259. So let's see, and computing hash f&v every time. And now I'm gonna say the other one is gonna be, oops, and computing f&v hash only once by using node key. Okay, nice. So I have this thing. Well, it seems that it worked. Seemed like it worked. So I mean, not huge say time saver, and also interesting enough. I mean, it does use a little more space, more allocations. It does use more allocations, bytes per operation. 108, 9. But then the number of allocations is the same, but the bytes is different, but not that much, to be honest. It's also not that much faster, but still, I mean, shaves it off. Try again. Okay, so this time is a little bit slower, but I think it's always kind of like oscillating. I'm gonna try again. Whew. Well, 258. Why not? I'm just gonna go for this. 258. Why not? I like it more. A little faster. Okay, so I think that's it. I think I'm gonna call it for today, but I think it was kind of an interesting thing. I mean, let's say before I call it, one thing I can kind of do is basically protect. So I think if we're gonna keep the GUID stuff as a key as a string, so GUID length, I think 36 characters, chars, 32 characters long. 42 characters long. So one thing I can do is maybe say like new node key perhaps. New key. And I can say this. Okay, nice. So now I can basically also scream here. So if len key is larger than 36, panic a key can't be longer than 36 characters. Okay, there it is. Nice. So node key. Let me say new key. You know what? Okay, nice. What's this complaining about? Ah, yeah, it's a pointer to the thing. So yeah, I don't need a pointer to the thing. Don't need a pointer to the thing. And okay, I think it's okay, nice. Okay, and right now I don't want to run a test for that failure case. And what's up with this? A key can be longer than 36 characters. Oh shit. Yeah, it's breaking now. It's breaking here. It's breaking all these tests, in fact. So I'm just gonna get the GUIDs. Get these motherfucking GUIDs over here. Replace this crap. Let's get it. Oops. GUID.string. There you go. Where else? Fine. Here I go. GUID.string. Okay, let me see if. Oh, come on. This is go test. Okay, it's passing. So what's this complaining? Oh, of course. I know. Yeah. Two 15. Yeah, why? Okay. There it is. Perfect. Just making sure there's nothing. Yeah, okay, nice. So okay, fine. Func test node key max there's exceeded t testing dot b. No, this is dot t actually. Um, I don't know, some long thing, some long thing here. And how can I catch a panic? Um, let's see. Let me see here. So go test catch panic. Okay, I'm gonna call this thing or copy paste this basically. Let's do this. Go test run. There it is. Nice. Now I'm just gonna make sure it breaks making sure everything is fine. Cool. Nice. Okay, so I think that's about it. One so one thing I want to do. Yeah, I could technically do another table, but I don't want to do this right now in the call. Not in the call, but on this recording. Yeah, but essentially this is not that bad because like if I go like for example 258 divided by um, is essentially yeah all of this per operation per operation. So it's basically yeah 258 nanoseconds per operation. So if this took if inserting in a million elements over 100 basically times on average takes so 258 nanoseconds. 258 nanoseconds, I think. Yeah, I think that should be correct. Okay, so yeah, I think I'm gonna leave it for today. So I think this is practically yeah basically almost finalized. So I think I covered a lot of ground for today. But yeah, nice. So if you've been following along all this time, I hope you've had fun and maybe see you next time. Take care, and I'm gonna go to sleep because as usual, it's very late over here. So see you later, guys.